What we know of as light, visible light, is part of a larger spectrum of electromagnetic radiation. So the electromagnetic spectrum is composed of electromagnetic radiation. Electromagnetic radiation is also known as radiant energy. And it's a continuous scale of waves that vary in their wavelength and their frequency. Now, the electromagnetic spectrum has these types of waves, these different types of radiant energy that are called gamma rays, X-rays, ultraviolet radiation, visible light, infrared radiation, microwaves, and radio waves. And these types of energy are different based on a couple of properties. The first property is their wavelength. The wavelength of a gamma ray is going to be smaller than the wavelength of a radio wave. Now we can see, looking at this chart, that the wavelength shown in meters, which is the number here on the top, is increasing going from left to right. Another way to describe waves is based on their frequency. The frequency is shown in the number that is below the chart here. And if you look at the frequency of a gamma ray, you'll see that it's much larger than the frequency of a radio wave. So the frequency doesn't increase from left to right, it increases from right to left, which is the opposite of how the wavelength increases. So we can say that wavelength and frequency are inversely related. Now, on this chart, you can also see an object above or very close to each type of radiation. And this is a way to visualize the scale of the wavelength. X-rays, for instance, are about as small in terms of their wavelength. X-rays have a wavelength in meters that is the distance, the diameter of an atom, whereas radio waves have a wavelength in meters that's about the same scale as a human. Visible light takes up a very narrow region in the electromagnetic spectrum. It is from 380 to 780 nanometers, so it's only 400 nanometers wide, a very, very small part of the overall electromagnetic radiation spectrum. Now, let's take a look at what makes these different types of radiant energy different from one another. The two properties that we discussed that make the radiation different from one another, the first one is called the wavelength, and the second is called the frequency. Now, if you pick any two waves, wave peaks, in a wave of electromagnetic radiation, the distance between those two peaks is called the wavelength. The wavelength is shown as the Greek letter lambda, and the wavelength is measured in some unit of length, and it's usually meters or meters with some metric prefix. Very common are measurements in terms of centimeters or nanometers. Now, frequency is the number of wave peaks that would pass a given point per unit time. And the frequency is inversely related to the wavelength, so as wavelength increases, frequency decreases, and vice versa. The frequency is shown as Greek letter nu, and it is measured in the units per time, where time is most commonly seconds. And so our units of frequency are going to be inverse seconds, so seconds to the negative 1 power, which is equivalent to 1 over seconds, And this is also the same as what's called a hertz. And so the unit hertz is abbreviated as capital H lowercase z. Spelled out, it's H-E-R-T-Z, where 1 hertz equals 1 second to the negative 1 power, inverse second. Another property of waves is their amplitude. If you take the waves of an electromagnetic radiation, a type of electromagnetic radiation, and you divide it in half, the distance from the half to the peak is called the amplitude. Now, amplitude is not a characteristic property of electromagnetic radiation. It is just a measure of the intensity. So a light that is very bright would have a greater amplitude than light that is more dim. Frequency and wavelength, however, are characteristic properties, meaning that they can distinguish different types of electromagnetic radiation from one another. So here on the bottom of this slide, we have 2 types of radiation. We have violet light, shown here on the left, and infrared radiation on the right. Now, violet light has a shorter wavelength of 400 nanometers. Infrared radiation has a longer wavelength of 800 nanometers. As a result, violet light has a frequency that's twice as great as that of infrared radiation. So it has half the wavelength and twice the frequency. Alright, so let's take a look at these 2 waves and describe them in terms of frequency, wavelength, and amplitude. And then we'll discuss which would represent blue light and which would represent red light. Okay, first let's look at the wavelength. We need to make a couple assumptions. The first assumption we need to make is that this scale, so these purple dashed lines that I'm covering in red, that this scale is the same length. And if we were to look at the wavelength then, the measurement between the 2 peaks here of 2 consecutive waves would be the measurement of wavelength. Our wave in A should have the greater wavelength because the distance is bigger than the wavelength in B. And so for A we have the greater wavelength. And B we have the shorter wavelength. I should say longer, not greater wavelength. Now, the other assumption we need to make is that if we were to measure the number of peaks that pass through some point per second, that these waves are moving. And we need to assume that the waves are moving at the same speed. And that's correct. That would be called the speed of light, which we'll discuss in a minute. But we just need to realize that they would be traveling at the same speed. Now, waves with a longer wavelength are going to have a smaller frequency. And that means that fewer points are going to pass through that point per second. So longer wavelength equals smaller frequency. Shorter wavelength equals greater frequency. And now finally, let's look at amplitude. Amplitude is the distance from half the height of the wave to the peak. If we look at the 2 waves, visually it seems that wave A has the shorter amplitude. And wave B would have the higher amplitude. And so that means that if this was visible light, wave A would be dimmer and wave B would be brighter. Now remember, amplitude doesn't characterize or distinguish different types of radiation from one another. You could have different types of radiation with the same amplitude. Now what's next? Which would represent blue light and which would represent red light? Well, on the electromagnetic spectrum, blue light to red light is only 400 nanometers wide, where blue light is at a wavelength of closer to the shorter wavelength end of the visible spectrum. Now that shorter end has a limit of 380 nanometers, so that's actually the violet light. And then the red ends at 780 nanometers. So our blue light should be at shorter wavelengths, and our red light should be at longer wavelengths. So our blue light would be B, because it has the shorter wavelength, and our red light would be A, because it has the longer wavelength. Okay, let's answer some questions. But before we answer questions, we need to just write out a couple relationships. We can write out in equations the relationship between wavelength and frequency. Now, wavelength times frequency equals the speed of light, and the speed of light is a constant. How this works is that for any wavelength with the units of meters multiplied by any frequency with the units of inverse seconds, you would always get a constant with the units meters per second. And the speed of light is about 3.00 times 10 to the 8th meters per second. Right, so we need to remember the equation that the wavelength times the frequency equals the speed of light. You can rearrange this equation in terms of any other variable. For instance, in terms of wavelength, the wavelength will equal the speed of light over the frequency, and the frequency will equal the speed of light over the wavelength. And so these two equations also demonstrate that wavelength and frequency are inversely related. They're related by the constant, the speed of light. So as wavelength increases, frequency would decrease, as shown by this equation, or as frequency increases, wavelength would decrease, as shown by this equation. Okay, so we can use this relationship to answer the following questions, and I have 4 questions for us to go through. The first question is, what is the frequency of a gamma ray with a wavelength of 3.56 times 10 to the negative 11 meters? Okay, we are solving for frequency, and we're given wavelength. So we're going to use the equation that frequency equals the speed of light over wavelength. Now we need to be careful in these equations with these types of calculations, because anytime we're given wavelength, we want to make sure that the units are in meters. And here we have meters, so we don't need to convert to meters. So we can plug in our constant, the speed of light, which is 3.00 times 10 to the 8th meters per second. And then we can plug in the wavelength that was given to us, 3.56 times 10 to the negative 11 meters. And we just have to divide the two. And once we divide them, we get the answer 8.43 times 10 to the 18th. And the units are inverse seconds, or you could say the units as hertz. Now the way we get these inverse seconds, I'll show down here. So we're dividing meters per second by meters. When you divide by something, it's like multiplying by the reciprocal. So we're multiplying meters per second times 1 over meters. The meters cancel out, and our units would be 1 over second, or seconds to the negative 1, or hertz. Our next question is, what is the frequency of a radar wave with a wavelength of 10.3 centimeters? We're given wavelength and looking for frequency again, so we can relate frequency to the wavelength by saying the frequency equals the speed of light over the wavelength. Now, because we have a constant, the speed of light, which is 3.00 times 10 to the 8th meters per second. In order to use this constant, we need to make sure that any wavelength or frequency that we're given and using with it has the units of meters for wavelength or inverse seconds for frequency. Because we're given wavelength in terms of centimeters, we need to convert it to meters so that we can cancel the units out with the units for the speed of light. So we need to take our 10.3 centimeters and convert them to meters. So we know that there are 100 centimeters in 1 meter, and so we can say that 10.3 centimeters is equivalent to 0.103 meters. And so we'll divide our speed of light in meters per second by 0.103 meters, and we would get the answer of 2.91 times 10 to the 9th inverse seconds, or hertz. So we had to cancel out meters, which is why we needed to make sure that our units of wavelength were in meters. Next question. What is the wavelength in meters of an FM radio wave with a frequency equal to 102.5 megahertz? All right. So we have a frequency and we want to find a wavelength. So we will use the other form of that equation, which is that the wavelength is equal to the speed of light over the frequency. Here we want to make sure our speed of light is always in meters per second, and then our frequency would be in terms of 1 over second. That means when we divide our units, when you divide by something, you're really multiplying by its reciprocal, and so we would get our units in terms of meters. So we need to make sure that our units of frequency are either in just hertz or just inverse seconds. Here we have megahertz, and we need to convert to just hertz. So we are going to take our 102.5 megahertz and convert to hertz. In 1 megahertz, there are 1 million hertz, 10 to the 6th hertz. And so when we multiply 102.5 by 10 to the 6th, we get 1.025 times 10 to the 8th hertz. And so that's what we can plug in for our frequency. Our wavelength then will equal the speed of light, which is our constant, never going to change, 3.00 times 10 to the 8th meters per second, divided by our frequency in hertz or per second, 1.025 times 10 to the 8th. I'm going to just write inverse seconds. Now our inverse seconds cancel on the top and the bottom. And when we divide the speed of light by our frequency, we get the answer 2.93 meters. All right, one more problem. What is the wavelength in meters of a medical X-ray with a frequency of 9.55 times 10 to the 17th hertz? Okay, same idea. We're going to say that the wavelength is equal to the speed of light over the frequency. Our frequency is given in terms of hertz or inverse seconds, and so we can just plug it in. Our speed of light is 3.00 times 10 to the 8th meters per second. Our frequency is 9.55 times 10 to the 17th hertz. And remember, 1 hertz is 1 inverse second, so they're the same thing. So our hertz or inverse seconds will cancel with our per second on the top. Dividing by the speed of light, or dividing the speed of light by the frequency in hertz, gives us the answer with the units meters. And our answer is 3.14 times 10 to the negative 10 meters. So our wavelength is much smaller of an X-ray than it was of an FM radio wave.